Hello, Manchester Robotics. We are here to present our final challenge. Our project focuses on controlling the angular velocity of a DC motor while interfacing it with a ROS2 system. To tackle this, we divide our work into teams: electronics, embedded, and high level.
Let's start.
The high-level team handled the raw systems, interconnecting nodes, defining setpoints, and ensuring smooth integration, while the electronics and embedded team focused on micro-ROS, writing the embedded code, and working with the ASP32 microcontroller. Even though our tasks were different, we constantly updated each other and shared our learnings.
So, what was the problem we needed to solve? Our goal was to design and implement a control system that could regulate the angular velocity of a DC motor while maintaining efficient communication between an embedded system and a ROS2 based high level controller. This meant ensuring the motor responded accurately to commands and that the system remained stable under different conditions.
To achieve this, we follow a structured approach. The ESP32 microcontroller was responsible for low-level motor control, receiving commands from the ROS2 system using micro-ROS. Meanwhile, the high-level system took care of setting target velocities, monitoring real-time performance, and ensuring everything worked as expected. This modular approach allowed us to separate concerns effectively and focus on different aspects of the project without overlap.
Now, let's talk about how the program actually works. Since we used ROS2, we can easily visualize how different components communicate. At the core of our system, we have a set of ROS2 nodes exchanging data in real time. One node is responsible for sending set points, another for handling control logic, while the controller runs inside of micro ROS. This structured communication ensures that each part of the system performs its role without interference.
When it came to tuning parameters, we went with a simple and manual approach. In this occasion, there was no need to get theoretical. We first started with our KP. We noticed that a big one would cause vibration, so we chose something low. We then proceeded to see a stable state error, which we diminished with the KI parameter. Finally, the KD parameter remained really low, just enough to diminish the oscillations, although there were some dispersible ones due to the way we were measuring the velocity and the quantity of the steps in the encoder.
A key aspect of our implementation was defining a control strategy. Since we didn't want to test only on step velocity changes, we implemented new setpoint modes. For example, a square signal, and also a sine wave. With this, we could test the response of our controller in response to the system.
Of course, every system has its strengths and weaknesses. One of the major advantages of our approach was the seamless integration with ROS2, making it highly scalable and modular. This means future improvements such as adding more advanced controllers or additional sensors can be incorporated without redesigning the entire system, which, by the way, was way easier to us since we involved the use of namespaces and parameters for the setpoint node. However, there were some challenges too. The communication between the embedded system and ROS2 introduced slight latencies, and the ASP32 processing power compared to the PC running actual ROS limited the complexity of algorithms we could run directly on it.
Now, let's look at the results. After implementing and tuning our system, we achieved stable and responsive motor control. The motor control successfully followed different velocity set points and maintained accuracy over time. When we compared our real-world implementation with the simulated model, we observed some differences, primarily due to unmodeled factors like friction and hardware imperfections. However, the overall performance closely matched our expectations.